Thank you, John, and thank you to the committee for nominating me for this award. It's a pleasure to be here this evening, and I'm hopefully going to give you a good introduction to concrete and what I was doing during my PhD. So the reason why I'm focusing on this topic is because we do a lot of testing on our construction sites for concrete every year, over 1 million tests in the UK alone, but there's a significant cost to the poor quality of concrete that we have in the UK. So you can see here it's in the billions of pounds of cost to us as taxpayers, to us as users of infrastructure. And so I thought we need to do something about this. So I'm going to start by telling you a bit about concrete itself. So concrete is a complex fluid initially, and I'm going to talk about what that means in a moment. But you're probably more familiar with concrete in its form like this. So all around us we can see concrete. Churchill is quite a famous example of concrete architecture, but we see it in bridges. It's probably even at your school at Abbey Wood. So it's a fundamental part of our infrastructure. And I believe that if we better understand the fluid properties of the concrete when it's in its early ages, we can better detect quality control issues, and that our current testing is a wasted opportunity to be able to do this. So that's where my PhD came in, and that's what I wanted to tackle. But I said that concrete was a complex fluid. Now, what does that mean? So we're very familiar with fluids like water, and we characterize those as Newtonian fluids. So when we pour water into a jug, it flows very easily. Now, you've probably all been there where you're bashing your ketchup and it won't come out of the bottle. That is because it has non-Newtonian properties, and this is a different class of fluids which concrete falls into. So it has a very complex behavior that we don't really understand, and the one way of understanding it is by understanding the rheological properties, and that is the yield stress and the viscosity. And I'm going to talk a lot about these properties as we go through this presentation. The yield stress is the stress that we have to put into a material to get it to move, so that's us bashing the back of the bottle. And the viscosity means that even when it does start to move, it doesn't flow as easily as water, so you have to spread the ketchup, it doesn't flow readily. And we have to be able to understand these properties if we're to understand the behavior of complex fluids like concrete. Now, the way we measure rheological properties is through something called a rheometer. And the Oxford definition is that it's an instrument for measuring the rheological properties of a substance. So I'm going to return to this at the end of the presentation, but just bear in mind that that's what I'm focusing on. And rheometers look a bit like this. So these are two rheometers on the left-hand side of your screen, which are used for concrete materials. So they're quite complex lab instruments, so you wouldn't see them in general practice. You definitely don't see these on the construction site. And there are some mathematical models which relate the stress to the rotation speed, but I'm not going to go into the detail, but what we're interested in is these two properties of yield stress and viscosity. So these are the instruments we use to get those. Just to say that those are the properties we need if we're going to understand the concretes we're using. But these are really expensive. They cost about £30,000 each. They're very complex. You need a PhD to be able to operate them, and they are quite impractical for construction sites. So the question is, what do we actually do? Well, believe it or not, we actually build sandcastles. So you've probably all been on a beach and you've put sand into a cone and lifted it away. And what you see is something like this. So this is actually concrete that's been put into a cone, and when you lift the cone away, it moves, and that's what we actually measure. And some concretes will move more than others, and that's the property that we use to describe the concrete. It's very rough and ready, but it does the job at the moment. What I will say is that we have different classifications of concrete, and this is about as much information as we can get about the fluid properties. So this is quick, it's simple, it's cheap, but it doesn't give us the rheological insights we need. So does it serve its purpose? I think it doesn't, but I'm going to use it because essentially this is used on every construction site in the UK pretty much every single time concrete is delivered. So I'm going to see if we can improve this and get the rheological insights we want. Now, when we conduct the slump test, this is what we see. So I call this the Mexican hat, and essentially There are three things of interest. The first thing we can measure is the slump, which is the difference between the height of the cone and the height of the concrete. But me and a few other researchers noticed that actually there are two different regions here. There's a portion of material that we call the unyielded region, and there's a portion of material that we call the yielded region. And one of them doesn't really change shape, which is the measure of H naught, and one of them clearly has deformed and changed shape, which is the ZY property. And using some quite simple force balances, what we see is that the yield stress of the material can be related to the weight of that unyielded portion. So basically, that little top of the Mexican hat is what's causing the bit below to move. So we can say that that's related to the yield stress, and I said at the start that the yield stress was the force that you had to put into a material to get it to move. So practically, it's the top of the Mexican hat. There are other properties that are of interest, so the diameter of the top, the diameter of the bottom. It's quite a complex picture. A further thing that I haven't spoken about is that this is actually a four-dimensional effect. So when you lift the cone away from the concrete, it deforms. But not every concrete deforms in the same time. So you can have very similar concretes that take different periods to come to a stop. Now, I'm not going to go into the maths, but just to say that there are many different variables here. And you can use something called dimensional analysis, which is a very powerful mathematical tool to actually work out what's of interest here. So I essentially derived a set of equations that I would then look to validate. And this allowed me to work out the relationships that were most important. So just to say that all of these geometrical parameters are in 3 dimensions, and time is very important. Now, I'm going to talk now about how I measure in 3 dimensions and how I measure time, because that's the contribution that I made in my PhD. So starting off with, how do you measure things in 3D? Well, some of you might be familiar with 3D scanning. So I thought of a method of actually digitally reconstructing the slump so I could take measurements of it. So you see here, this is not a video of an actual slump test. This is a 3D reconstruction that's been computer generated. And what this allows me to do is to take measurements of any property that I want on the face of the concrete. So as I was mentioning, it's the H naught property, the unyielded height that I'm interested in. And you can see using the example at the bottom that I can quite easily measure that property of the Mexican hat. So when I said that these tools were related and that you can predict the yield stress of the material that we have, just from conducting the standard slump test, what I'm going to do is I'm going to compare on this graph the results from the very expensive rheometer on the bottom versus the 3D reconstruction in my experiments. And what you can see is that essentially you see a very good relationship between the two, which suggests that both of them give equally good results of predicting the yield stress. And I can simplify the equation that's on the screen to something that's very simple, which essentially is that equation that I was showing at the start. So it's my rho GH. This is a validation that that physical relationship holds for the concretes. Probably more interesting is how you measure time. Now, there had been many, many different proposals to measure the time of the concrete moving. All of them were very intrusive, and as I mentioned, this test is embedded in everyday practice, and people didn't want to change the test. They didn't want anything that was invasive, so I came up with a new idea of using a wireless accelerometer that would allow us to measure time, and that's what you're showing on the screen. That's an accelerometer. And this is what it looks like. So when the concrete, imagine this is you doing your sandcastle test. You basically put the accelerometer on the top of the material and it follows the material movement. This is quite powerful because what it shows you is that you can measure the acceleration of that material over time. So before lifting the cone, you don't see any acceleration at all because it's not moving. When you lift the cone, you see a big jump in acceleration because it started to move. And then after it stopped moving, you don't register any acceleration. So essentially, you can understand the time of movement from that. And then if I do what I was doing earlier for yield stress, but I look at viscosity, I'm not going to go into the details of the mathematics and the equations, but what I'm going to say is that viscosity I understood was a relationship between the yield stress and the time of movement. I just told you that I can understand yield stress from the 3D scanning method and that I can measure time using the accelerometer. So using those two things together, I can understand viscosity. So on the bottom axis, I'm showing you the viscosity measured from the rheometer, the very expensive method, which is what I want to get. And on the other axis, I'm showing you the viscosity derived from the slump test, which wasn't previously thought possible. And if I add in the results from my experimental test, you see that they agree quite nicely, so that it suggests that this is a much more accessible method to obtain viscosity. And just to say that what I concluded in my PhD was that by adding simple digital technologies to the existing test, you could completely transform the insights that you got. So previously, you wouldn't have the accelerometer and you wouldn't have the 3D scanning, but with those two tools, you can understand geometrical measurements and you can understand time. And with those two things, you can derive yield stress and viscosity, which are the rheological properties that I need. So if I return to the definition that I said earlier, a rheometer is an instrument for measuring the rheological properties of a substance. With these digital additions to the standard test, I believe that for the first time, this very crude and simple test has been transformed into a rheometer which meets the standard definition that's been set out by others. And through various different testing that I've done, I found it to be 90% accurate compared to the very expensive and advanced lab instruments, but it's potentially 10 times cheaper, so it has much more propensity to be used on construction sites, and it's much more appropriate to that end. So that's a whirlwind tour of the work that I've been doing. Thank you again for the invitation and the prestigious slot before Robin's talk, so I really appreciate it. If there's any questions, I'd be happy to answer them.
Thanks very much, Callum. There's a couple of mics available. Just put your hand up if you'd like to ask a question. I'm going to ask a question first, though. Have you tried it actually on site with building workers, construction workers?
This is quite a common question. So that's the next phase of the project. So we're probably sitting at technology readiness level for those that are familiar around 4. So the next step is to basically get into real site lab, outside of the lab and onto real site environments and to do user testing. So one of the things I was keen to do in the lab was actually to get others to use these tools and to verify that I can use them, okay, fair enough, but can other people use them? Because I take your point that a lot of construction, there's different skills, there's different experience levels, so that is a very pertinent point that will follow on in the next step of the project.
That's a very diplomatic way of putting it, I think.
No, thank you. That was exceptionally interesting. You started with a couple of super facts. One which is that this costs the UK £10 billion a year in concrete-related costs. The other is that if you can understand concrete rheology properly, then you have a much more accurate model. So I'd be interested to hear your insights into how the results you've obtained affect that £10 billion a year figure.
Okay. So that £10 billion a year figure has been derived basically from an error and a waste rate of around 5 to 10%, which we believe is accurate for the UK market. And through this, because essentially probably about half of that figure is because the concrete exhibits poor performance as it gains strength. And I believe that through this you can relate the rheological properties to the strength development. And by knowing that, you can essentially reduce those issues in the long run. You can refine the concrete mix so they don't occur, but also often what happens is that it has poor placement performance and people don't detect it when they're doing the slump test. I don't know how familiar you are with the market, but essentially then what happens is they don't actually intervene, they just keep getting the concrete loads delivered, But what I'm hoping through this is that they can send feedback to the batching plant so that when the next load is delivered, it's actually refined and that the placement gets better. But I would say probably about half of the figure, so about 5 billion, is affected by this specific issue. Yeah, thanks.
I'm interested in the slump test, how it affects the curing. Obviously, concretes, I mean, I can buy a rapid cure, which will not slump in a few minutes after I've put it into your cone.
Yeah.
And how does it affect the actual ultimate properties of cement, and how it affects how do we know that cement is fully cured? Does it give you some indication as to a fully cured concrete with the ultimate properties that you're looking for?
Yeah, so it's a good question. I should probably caveat this answer with that because you've not been able to measure rheological properties of concrete at scale, some of these questions are still not known. So it's thought from the early work that I've done that there is a relationship between these early age properties and the strength. So through some of my work that I've been doing with the physics department, we've been able to quite accurately predict strength by adding in some of these properties into predictive tools. But to answer you, I'm kind of sidestepping your question, because what's hoped from this work is that because we can get a lot more data and information about the rheological properties, because we can now measure at scale, these questions will be the next step. So like as I was saying earlier, there's two forks in the road from the work that I'm doing. There's the one that is getting this onto construction sites, getting it feasible and getting it used by practitioners. And the second is fully unlocking the data that this holds and feeding it into later prediction. So I think the last two questions are probably linked, that the full benefit of this is not yet known because we've not had this information at scale in the past, but we now do.
Any more questions? Okay. Thank you very much, Callum, and good luck with the 10 billion.
Thank you.